Assalamu alaikum. So today is day 4 on 13 summer school on LHC Physics. Today's many more interesting lectures by the foreigners like Thomas Muller from Germany and Zafar Yaseen from Pakistan Atomic Energy Commission and many other foreigners. So today's I think it's a good day. So I'm on the way. So stay tuned with me. And I want to say that no matter how tough the journey gets, your persistence will crave the path to victory. Thanks for watching. Stay tuned with me.
Best to give me your loyalty, 'cause I'm taking the world, you'll see. They'll be calling me, they'll be calling me royalty. Best to give me your loyalty, 'cause I'm taking the world, you'll see. They'll be calling me, they'll be calling me royalty.
So we start with an initial configuration, we can randomly pick it, and then we make some updates. And okay, these updates, making update is you have to worry about how to update, because if this is you are randomly choosing these configurations or these paths, but they have to be decoded again. So you have to make certain updates and then see if they are decoded enough. And only then you can examine. And then once you have made enough updates, you can evaluate the bar if this is good enough. And if this is good enough, you proceed to see if the initial starting point has been forgotten or not. If it has been forgotten, okay, you proceed to the measurement. If it's not, or if it's rejected, the configuration, you go back and make another update. And this is how the code works. And this box, this is usually what people usually worry about, how to make configurations and analyze them. For us, we use Metropolis. Kind of cousin of Metropolis. It's called multi-piece Metropolis, but what it does is that it goes to one point and it changes the field, and then it analyzes the whole configuration, and if it's good enough, that is the action is smaller, it checks, it considers it for further evaluation. If not, it goes back, or it sees whether it can be randomly chosen or not, and if it's also rejected, then it goes back to the update. And once you have performed a measurement, obviously you are calculating an average value over a lot of samples. So you need to go back to get another sample. And this is how the code works for us. And in Lattice, pretty much any Lattice code goes pretty much like this. Okay, so for our model, we have this model. So we have a real singlet. So of course, this is the real singlet. We have a Higgs, an SU2 structure, which is this one. Notice that the minus sign is there. I didn't put it a positive here because the problem that I mentioned has nothing to do with the Higgs mechanism. So of course, if there is, well, we are not worried about Higgs mechanism. One can just write a minus sign there. And there is another reason I would like to extend the theory further for some other research. And this theory, these stuff will provide a kind of a baseline for further research. So I thought it's better to just leave it like this. But this, if you put it to plus sign, it will, switch on the Higgs effects, and this is also something that I have to worry about, but not in this discussion. And of course, if we are thinking about the renormalizable model, then of course these are the interactions in the equation model that you can write, and we have to change the values of these lambda, alpha, beta, and gamma, and see what happens, and calculate the quantities and stuff. So if you reprogate the whole thing, so you get this thing, and if you you need to make you need a lattice version. So actually what you do is that you say that okay, this point is actually a number times something that has physical meaning, and okay, in the same way, you can also write like this, these quantities, they are nothing but the dimensionless objects multiplied by the lattice spacing or inverse of lattice spacing, which is cut off to take care of dimensions. So good thing is that if you do that, well, we have a very interesting result. We have an action that does not depend upon anything that is physics. So it's just numbers, because you have taken out the dimensions. So if you have taken out the dimensions, then what you are doing is playing with numbers. And this is a very interesting part of the lattice field theory, because without you have numbers, you can play around and you can calculate the results, and then you worry about this A thing, the lattice spacing. It's a tricky business, but good thing is that we can still do it. So once we are done with that, this is the action that we worry about, and remember that there are minus signs. So for example here.
We discussed how the different detectors enter in the muon tracker momentum measurement and the role of the magnetic field, and now we put together the different phases, right? So there are basically three main algorithms for reconstructing muons. Here we are assuming muons are directly coming from the proton-proton collision vertex or close by. There is a separate family of algorithms for very displaced muons, meaning muons that are produced by long-lived particles, so they can basically be produced anywhere in the detector. So this displaced muon use case requires dedicated reconstruction. I won't have time today for discussing this, but if anybody is interested, I can of course point to the relevant papers and material. So for muons produced, let's say, within the inner tracker detector, then we can reconstruct them either using the outermost chambers, which we call standalone muon reconstruction, where we basically start from a segment in any of these chambers, and then we propagate the segment to the next chamber, refitting the track, refitting the trajectory hypothesis, knowing the magnetic field. Since only muons can reach the outermost part of the detector, we can be somehow confident that these are muons. Then there is another algorithm which is called the tracker muon reconstruction. Here what we do is that we take the track reconstruction as we discussed yesterday, where we only use the silicon tracker. and this produces a lot of possible tracks for any charged particle, and then we propagate the track to the very first muon chamber. Since only muons can traverse the solenoid, then okay, we can say this is a charged particle, but this is also a muon, okay? But we are not fully exploiting the rest of the muon system. And this is useful for low-pitting tracks. Finally, when we combine both, we call it global muon reconstruction. This is done both propagating the inner tracker to the muon chambers and then with an outside-in approach, propagating the standalone muon track to the inner tracker and then repeating the combinatorial track finder approach. This refit is actually the best we can do with the CMS detector for identifying muons and most importantly measuring the curvature, so the momentum. These muon reconstruction algorithms also enter in the particle flow. You should have learned about the particle flow in the jet classes. Here the idea is that instead of reconstructing the objects separately for different families, let's say electrons, muons, jets, etc., you look at your detector as a whole. You split the detector in geometrical regions in the eta phi space. For each region, you cluster together objects that share something. In each, so the geometrical region is called block. So in the block, you run your reconstruction algorithms for muon. That's the same as I discussed in the previous slide. And then every time you identify an object, then you take it out and you loop on the rest. So you have a comprehensive view of the physics in each geometrical region. This is called particle flow, and this is very powerful because it allows for connecting all the objects. So, for example, we are reconstructing muons, but we also know how much activity is in the calorimeters surrounding the muon, so we can define what we call isolation, that I'm going to define better in a few slides. Now, for closing this part about the reconstruction, we should look at the specific algorithms for determining the muon PP. Here is just to give you the names of the things that you might encounter when dealing with muons in CMSSW, in the CMS software. We already discussed about the physics of the detector, and we know that unless we are dealing with very high PT muons, the muon PT is the resolution is driven by the silicon tracker.
Just getting started, my eyes on the target now. You're the better ones, you can't go.
Of the two systems and the inner tracker only, and then at IPT, you really improve the resolution when you combine the two detectors information. Okay, so this closes the reconstruction part, and now we start looking at the usage of muons in the analysis. In order to indeed use muons in the analysis, we should for sure distinguish between muons depending on the production mechanism. In general, when we speak about prompt muons, we think about muons produced very close to the proton-proton interaction point, coming from on-shell WZ, its boson decay. Tau decays can produce prompt muons or close to the prompt muons, so the displacement will be very, very small. So you do expect muons coming from the primary vertex, meaning close to the proton-proton collision point, quite isolated, meaning that you don't expect any more particles to be produced collinear with this neon, because this has quite high energy. On the other hand, if you are working on D physics, so you are dealing with D and B mass in this case, then you do expect muons to be produced a little bit far away from the primary vertex. We are dealing with particles that have a lifetime of the order of a few picoseconds, so they travel a bit in the inner tracker. And typically these particles are decaying into muons and something else, so you don't expect the muon to be isolated. And the PT of these muons in this case is quite small, let's say below 10 GeV. Then you might deal with light flavor decays instead. Here I mean K and pi, which can decay, as you can see in the diagram here, to muon neutrino. This is this is often the background for many different analyses, especially at low PT. When a particle decays to muon, in the detector you will basically see a muon trap, because you do expect only muons to reach the outermost part of the detector. How can you identify these cases? Well, in the point where the K decays to muon and something else, you do expect a small deviation in the traffic. So this is, you won't be super smooth, but you will see some what we call kinning. And this can happen either inside the inner tracker or between the inner tracker and the muon chambers. This means that our traffic extrapolation will not be very good for these muons. Finally, you might have, this is let's say rare, but it happens, hadrons being misidentified as muons. As you know, charged hadrons should be stopped in the hadronic calorimeter. But sometimes, for very high energies, they can reach the muon system, we call it punch through, and then the quality of these tracks should be much lower than the actual muon tracks, but this is the only background source that is not real muons. This is something else identified as muons in CMS. And here you can see how these families, let's say, distribute over the muon PT from simulation. Prompt is, let's say, dominating a higher PT, while heavy flavor decays has a larger contribution at low PT. In the gray region, you have everything that is not in the previous categories, so K and pi decay in flight, punch through, but most importantly, this plot also contains pile-up muons. Muons that can be good muons from interesting decays, but they are not produced in the proton-proton collision we are interested in. They are produced in the proton-proton collisions that are overlapping. This is very important contribution, especially in run 3 where pile-up is higher. Now, we should build our toolbox for identifying the muons depending on our analysis needs. The ingredients we have in hand are all the hits and segments that we use for reconstructing the muon track. So for the inner tracker track, we have the hits in the pixel layers, in the strip layers. Then in the muon chambers, we can also count how many segments did we use for reconstructing the track. The higher these numbers, the better the quality of the muon track. Then whether we look for a muon produced promptly, so compatible to the primary vertex, or produced from a displaced vertex. So here we simply look for tracks within a cone distance at the touch distance, surrounding the muon, and we count the PT of the tracks around the muon divided by the muon PT. So this is the simplest thing that we can do, but this is not taking into account neutron particles, activity in the calorimeters, and so on. Then let's say the most commonly used isolation is the particle flow isolation. You can see the formula here, and there are more details in that. is that you not only take into account charged particles, but you also take into account neutral particles, photons, and you subtract this contribution, so half of the amount of the charged particles, which corresponds to the pile-up contaminations. This is motivated by isospin symmetry, because you assume the ratio of charged to neutral pions to be 2. So this is making, let's say, on average, the charged to neutral the charged to neutral particle contributions in jets. So you subtract this to take out the pile-up, and you can see more details here in the paper. This is called delta beta correction. And then there is even a more complicated implementation of this, which is called mini-ISO, which is a delta beta corrected isolation with a cone size which is not constant. As you see here, it's always 0.4. It's dynamically dependent on the BT. So for boosted topologies, we'll have a different delta. And finally, Papi-weighted objects can also be used for computing isolation, taking into account the pile-up, hopefully removing this for, let's say, letting you know how many ways you have to distinguish between isolated and non-isolated muons, and then you will deal with this for specifically for your analysis. Yeah, the idea is to give you all the references here for having the formula and knowing how these variables look like. Okay, now for the muon identification, in my previous list we had some MBA things, if you remember. These are actually the most recent developments in terms of muon identification, and this is going to be the standard in the next runs of the LHC at CMS. The idea is that you use multivariate analysis for combining all the different variables we already discussed, number of pixels, number of segments, chi-squares, kink, segment compatibility, isolation, and so on, impact parameters. Instead of cutting on these variables, so doing a cut-based ID, you train a machine learning model. What we use is supervised learning. More typically, we deal with cross-GBoost abilities or simple neural networks, so nothing fancy. The idea is that you give your model examples of labeled data, so you know what is background, what is signal, and a list of variables. You want the model to classify your background and signal, and the classification is done by minimizing a loss function, which is which is comparing the labels that you already provide to the model to the predictions produced by the model. And so in terms of machine learning technologies, we use quite simple things. We recently published this paper where we document the development of two different MBA IDs. One, we can call it a general purpose. So in this plot is called the muon MBA ID. Signal here was made of a cocktail of prompt muons from boson decays, tau lepton decays. So let's say isolated muons, not super prompt. But we are also including heavy flavor decays, which are also not isolated and non-prompt. So signal is basically including everything that is not K and pi decays in flight, punch through, pile up.
Cause I'm taking the world, you'll see. They'll be calling me. They'll be calling me royalty. Best to give me loyalty. Cause I'm taking the world, you'll see. They'll be calling me.
systematic uncertainties. What if this number is not exactly 0.98, but this is shifted? Because my fit is not perfect, because my fit depends on the PDF function I'm using, or it depends on the binning I use it for the distribution. It's important to indeed evaluate the uncertainties on the final efficiencies than on the final scale factors. Uncertainties can be statistical, depend on how many events you have for fitting the distribution, so for extracting the number. And it can be systematic, as I mentioned, so your target probe can be biased, the result can be biased by something like the functions you are using for modeling in the background, some preselections, or some binning, for example, choice in your mass distributions. Please be aware that uncertainties on the efficiencies are not symmetric. So whenever you look at an efficiency plot, you do expect the error bars to, let's say, be squeezed towards 1, because the efficiency, including the uncertainty, can't exceed 1. The correct way to evaluate these uncertainties is using binomial confidence intervals, which is already implemented for you in the T efficiency class in ROP. So you can look at how is it implemented and use the same in your analysis. And this is useful for any measurement you are doing, also in the lab, whenever you deal with efficiencies. Okay, now the last topic I wanted to cover is an additional correction that we compute in CMS and we provide to the analyzers in order to further improve the estimation of the muon momentum. The estimation of the muon momentum, of course, translates into the resolution for any mass peak that is built using muons, muon particles. Okay, so it's not only important to have a good knowledge of the muon PTs for casting on it, but it's crucial to have a good knowledge of the muon PT, because this will affect how weak is your mass peak in your final analysis. So what can be happen in the, especially when comparing data and simulations, is that you don't perfectly know detector alignment, or you don't perfectly know the magnetic field. These two effects typically cause a bias in the track reconstruction that is depending on the muon charge, because you can have a different bias depending on the curvature of the muon. It can depend on the geometrical region where the muon is reconstructed, because detector misalignment is not expected to be symmetric. So you should ensure that the data Monte Carlo are in good agreement in terms of muon momentum estimations. And this is why we introduce a further correction, which we call muon momentum scale and muon resolution scale. The idea, actually there are different algorithms. The two main ones are the Rochester algorithm and the generalized endpoint algorithm, the latter being mostly used for IRQT muons. So I will be describing the Rochester algorithm, which is very widely used. The idea in general is that you look at an interesting decay, for example Z to 2 muons in data Monte Carlo, and you should somehow force this is done in an iterative way, to force your simulated distribution to well model the data distribution. And you can see how the distributions look like before correction. You can see that the peak in data doesn't correspond to the peak in Z, so this is called momentum scale. So you have a deviation. and the widths are not also are not really matching. So this is called the resolution effect. After correction, we do expect the two distribution to match. The correction is implemented as a function of the muon PT, of course, but also as a function of the charge and of the observer rapidity and the phi angle of the muons, because, as I mentioned, the bias depends on all these three variables. And
They'll be calling me royalty. They'll be calling me royalty. Say I'm dangerous 'cause I forgot the cages. No, I couldn't take it. No, no. There are people that I guess they'll never learn. Every time I break, there's just more pain to burn.
अच्छा क्या कहते हैं, क्या क्वेश्चन? सर ने सर से पूछा ये जनरल सबसे पूछा ना, अच्छा तो जवाब सर ने दिया।
एक सर ने देखो फनी से बस वही जस्ट मतलब नाउ ना वो कुछ नहीं है ना कोई एक्सप्रेशन हो आज
एंड पे क्वेश्चन पूछेगा स्टार्टिंग में या मिड में?
जस्ट एक ना
मौत कर रहे हैं ठीक है उससे बस वो बात ये कोई आइडिया बना दिया तो जाके बच्चों को क्या रिकॉर्ड मैं एक बार दूसरे से बात किया तो मैंने पूछा उससे अगर आइडिया
किस पे लेक्चर दिया था? और उसका 2 है ना, मेरे पास 4 लेक्चर हैं, इसके 4 लेक्चर हैं टोटल, 3 है 4
उसका तो अलग ही
लास्ट सप्ताह में सारा फॉर्मूला मैंने देखा और उसमें वो लैब नहीं है, लैब नहीं है,
लेब नहीं है सारे लेक्चर
ये अभी हम अपना फर्स्ट टाइम है ना, एक दूसरे को और लेंगे हम चल सकते
हम उस साइड में काम करते हैं माइक और प्लेट
कोई है बोलने वाला?
नेम के नहीं शायद कोई
कैमरा बंद करके दे क्या आवाज में
अभी पहुंचे नजर नहीं आया ये 2 BS है ना,
मैंने कॉल की तो आपको बोलता है ऑर्डर किया था मैंने आपको दुकान की काफी तो चढ़ा है वो मैंने कहा थोड़ा सा कॉल करूँ
हमारी यूनिवर्सिटी से बस एक मैडम उसमें ही आती है सर यासिर, सर रहमान तो नहीं आते वो, क्योंकि वो है ना प्रैक्टिकल यहाँ पे जमीन वो असल है, असल में वो मुझे भी किसी ने कहा था कि अगर आपने पार्टिकल फिजिक्स में रिसर्च करनी है तो कायद-ए-आज़म यूनिवर्सिटी में जाओ, वहाँ पे जमीन असलम होती है। ये मुझे किसने कहा था? प्रोफेसर मसूद ने कहा था, वो हमारी यूनिवर्सिटी के HOD
हम पार्टिकल फिजिक्स ना वो बता रहे हैं आज साइड में काम ज़्यादा वो नहीं नॉलेज
देखते हैं एक्सपेरिमेंटल थ्योरेटिकल क्या हो गया?
नहीं मैं तो मेन के साथ ही कर रहा हूँ। यहाँ पे आओ ना, यहाँ पे
What detector are you using? Is it a full detector or is it just a silicon detector or a calorimeter? What are you simulating?
we are specifically
I see.
for synchronization.
Yeah. Okay.
We'll never, never, never
This is our Nadeem bhai. Nadeem bhai, what's your experience about 13 summer school on LHC Physics?
Their experience, my experience is very amazing.
It's day 5, so
Yeah.
how you can feel?
I am learning a lot.
A lot about LHC.
Yeah.
And this is our Sajjad bhai. Sajjad, how's your experience about?
Our experience was very good. Now further, we are looking forward to some interesting or some mind-boggling concepts about high energy physics. So let's see.
Okay, that's amazing. So now the talk of the Thomas Muller. Let's see. Okay, thanks.
So let me open a parenthesis here since we discuss also electron colliders after. How can you measure the mass instead of the classical collider? If you remember yesterday at the start, we said that about 20 years ago the precision in the measurement was dominated by the measurement which was done electron, which was in the classical collider. Now, in the classical collider, the process is relevant. It is a plus minus in W plus W minus, so you have typically pairs of W. You can have also single W's at electron colliders, but it is not convenient, the perception is lower, it's not convenient. So you have a pair of W, and since you can apply in classical collider the full energy of making conservation, also in the longitudinal direction, this you can impose the construction. Then we can really measure the invariant mass of the W, of the health, and the invariant mass of the W. So you can see that there in the picture which is there at the bottom on the right, you have a real bright Wigner which is convoluted to a Gaussian because of the solution effect. So you don't have a Jacobian peak, but you have a real peak at the W mass. So you have more statistical powers, and at the end of the day, the measurement done on left, which was dominated 20 years ago, it was done only with about 6,000 W pairs per experiment. Bear in mind that nowadays, for the measurement of Alton colliders at LHC, we're using millions and millions of W's. So I mean, even with rather small statistics, you can have precise measurements. Another information which which can be used for the measurement of W mass, it is the threshold scan. The W mass is around 80 GeV, so in WW production we have pairs, so you need to be around 160 GeV, of course, and we have this cross-section which is raising, and the point where the cross-section is raising is very sensitive to the value of the W mass, and to a lesser extent the width too. This was done at the time in 1995. However, the uncertainty was large about the number of EV because only about 20 events per experiment. So these are sensitive quantities of the statistics. So there are several methods. Summarizing, there are several methods for the measurement of W mass, and they are quite different from other colliders to electron colliders. Now, let's go again to the Hadron Collider case that we discussed first. So, what it is the challenge if you want to make a measurement with the precision of 10 to the minus 4? Now, clearly, you have to measure the PT scale with extremely high precision. So the measurements are dominated by the muons, essentially. Very high precision means we should reach an extent to the minus 4 precision. This can be done. It has been done by Atlas. It's been done. The calibration is already available public from CMS and to the minus 4 precision. This is essentially taking advantage of the fact that we have very high statistics at the JXI and at the Z suiting, but in this case to be independent from the information of the Z, which is used as a cross check, if you like. The JXI must be used, and using the high statistics of the order of 100 million JXI, you can control as a function of pseudo-activity and as a function of phi 2, as a unit factor 2, you can control the calibration of the PD scale with this very high precision. And then you unleash the disintegration energy, which is more difficult to control, so you need to align the measurement as much as possible on the PDO director. And then you have the theory part related to the fact that W can have a PT, and so you need some theoretical input there, and you should need to reduce as much as possible the reserve. Remember that again, we have the issue of the PDF that can be aware and be measured from the river themselves. We have seen yesterday that for the W we can measure the density and the charge of the charge differential distribution of the W, which are seen to control as much as possible. The process is the trial process, QT bar to Z, and then typically you use your pairs in the final state. So, how can you know the direction of the quark since you have the protons on one side or on the other side? So, I mean, clearly, these you have to take assumption from the PDF, you need to insert your knowledge of the PDF, and clearly, typically, if you go at higher rapidity, you have higher sensitivity, because typically it is the valence quark which is producing most of the trivial events at high rapidity. So you know that the valence quark can be a U or a D, so you have the direction of the valence quark. You can assume that it is from the proton, which is going in the same direction, in the same forward direction, and we have the anti-quark on the other side, and so you can, in that way, you can have a reliable assumption on the quark direction. So these, I mean, clearly, you have also contamination of events of opposite direction, where it was not, in spite of it was very forward, it was not the U-quark, but was some U-quark on the direction of the proton, which is in the direction. So I mean, you need to convolute your measurement with the PDF, the assumption of the PDF. It is very relevant, and it is the important systematic answer to this measurement of the asymmetry at LHC. So you need to define a reference frame. In the Classimanus colliders, the lab frame essentially is the central mass frame. Here we are not in this situation because these are particles which are very imbalanced, so we are moving reference frame, and so it is defined, it is used in order to have it as close as possible to the central mass frame, using the so-called Zafar coordinates axis, which are defined there, you can find described in various papers. essentially use the angular bisector of the proton and the other proton or antiproton in the case of theatron, and this bisector it can be shown that it is close, it's a proxy for the direction in the center of mass. In the case the differential angular distribution has many parameters, but if pt of the z is low enough, essentially we have one parameter only, which is relevant, which is related to the polar symmetry. So as you can see, it's a bit more complicated in other collider that is the measurement of polar symmetry. Anyway, it is done. These are results from CMS, where you can see on the right, for a certain rapidity beam, for environment mass beam close to the Z mass, you can see that there is a tiny asymmetry that by eye it is difficult to see, but it is there. And then you have the asymmetry really, for Neptune, the asymmetry is just a few percent, so it is difficult to see by eyes. At the energy, these few percent are the center mass energy corresponding to the Z mass, 91 GeV. But at different center mass energy can be decided on asymmetry. You can see there on the left plot, when you have the distribution, you see all these parts in the distribution correspond to different, and there being different center of mass energy, you can see that the symmetry can take large values which are far from the center. So, in conclusion, we have the experimental situation is the one which is repeated in the
calling me royalty. Best to give me loyalty.
remaining viable theories. Potentially, it would even investigate the coupling to the first generation in the direct process plus or minus 2h if you succeed in having being which are monochromatic enough. So even instead of so we could potentially see the peak of the X at the resonance. Then at HH we reach a zero mixed coupling of 5%, which means starting to understand the shape of Higgs potential around the medium, and with the precision top mass versus the Higgs, you can investigate even more the Higgs potential, and you know that this is related to the stability of the universe. This knowledge of the precise Higgs mass versus the Higgs mass, we have certainly seen the plot. Now, coming back to our subject, which is electronic physics. Now, as I said, we can have 5 other analyses more than that length. And this means improvements on many observables and valid observables, the Z mass, your factor 20, your factor 20 improvements with respect to the width, and the atomic width Rn, which is the relation between the atomic and atomic width of the Z, which is sensitive to alpha S. You have a factor 20, so not automatic in the determination of alpha S. For the three mixing compounds, which I mentioned before, it is 2 order of magnitude, what is foreseen. Then, if you remember when I mentioned yesterday that there is a parameter which is the alpha QE, which is part of the fit, which has to be determined at the scale of the Z mass. So this is done through dispersion relationships currently using the energy experiments. It has never been measured, and it will be measured for the first time at FCC, so there is an important parametric center that will be taken away, and then we do also another observatory or the number of three measurements, which is what we can do. So there is a key ingredient there. There are technological issues. So it's not just having W's of the bosons produced up with very high in enormous and huge quantity. It's not just a matter of luminosity. But there is something more. The fact is that you have the potential of knowing the central mass energy of the beam much better than it was done the previous classical accelerator collider lab. How it is measured the central mass energy, how it was measured, you have to reach the precision, the kind of precision of the atmosphere, etc. Well, and when you have a circular collider, there is emission of synchronous radiation, and this builds up a transverse polarization in the beam, and this is called the so-called thermal effect.
Will show that if you transform electric field by this general duality transformation, these Maxwell equations are invariant in space without sources. So this give you a hint how we can write the covariant form of source-free Maxwell equations. So we will use duality transformation. We will replace E by B and B by minus E. So if you do that, you get a dual tensor F tilde, and instead of E we have B, and in place of E we have B. So we get this equation. So, and there is no source. This is the source. 3, 4 equations where 4 derivative of F mu k is equal to 0. And now you can, as an exercise, you can see you can also write down this dual tensor F mu in terms of field tensor by this LH beta symbol. This is a totally antisymmetric object, and it carries the 0, 1, 2, 3 value is +1. So next we move on to Lorentz-Force law. So we know the Lorentz-Force law is F equal to Q E plus P cross P. So if you make this transformation to this Lorentz-Force law, you replace E by B and B by E, you get a dual kind of force. You can see it's charge times B and charge times P cross E. So you can add in Lorentz-Force law another term with magnetic charge, this first part, now we will add subscripts. This one is electric charge and this is magnetic charge. From this we can write down such that, and that these this Lorentz force, generalized Lorentz force, R is invariant under these generalized QRT transformation, where you replace electric charge with the magnetic charge like this, and magnetic charge with the electric charge. If you do that, these two terms will transform into each other, and the Lorentz force law will remain invariant. So, with charges, same is the case if you consider the Maxwell equation with sources. You can make it consistent like this. You have divergence rho E over epsilon naught. This one, the pole with electric charges and currents, and this one. Now you can have magnetic charge density or magnetic current, and from these two equations as an exercise you can see that this you can derive the continuity equation, which is a statement of charge conservation. Same is the case with this, and this equation you can write down in covariant form like this. So there is a duality transformation of Maxwell, of a generalized Maxwell equation. So we know, I mean, the B is 0 everywhere, but A is not. Same situation. So consider a charged particle go into state experiment, and you consider two pathways. So this condition for absence of Aharonov-Bohm effect tells you that the physics should be invariant, whether you take this one or this one, and then you can combine these two pathways. It will become a closed loop. And this invariance means this phase should be quantized to n pi. Then this phase vector will vanish, and this will give you charge quantization. Because I don't understand, I will speed up. So this was the Dirac monopole. This is singular. This is singular pole monopole. Now I will talk about another kind of monopole, which are usually called topological monopoles, and it will be related to models like grand unified models or electroweak unification models. And there, I mean, let's consider this first one, where basically two and books in separate papers showed that magnetic monopoles are generic feature of grand unified theories. What are grand unified theories? These theories try to unify the electroweak with a strong force. So here you can see they have considered a model which doesn't work, but you can call it a toy model proposed by Georgi and Glashow. This is based on SO3. SO3 is as a market to SO2. SO3 is a rotation, special orthogonal group, rotation group in free space, and this is as a market to SU2. So they tried, the Glashow and Georgi Glashow tried to unify electroweak unification, electromagnetism with weak force in SU2, simple group SU2. So there was no neutral current. The prediction of this model is no neutral current, but we have seen that there is neutral current. So this is a toy model, but it so they have considered two models in their paper. Islamabad model. At that time, people call it Islamabad, but no Glashow. Glashow is this. Glashow model is this. So electroweak unification model, but they know that there is no monopole in electroweak unification, Islamabad model. So they considered Glashow model. And Glashow model, I mean, this part is a bit involved, so I will skip the details. So only done for electroweak unification in SU2. So this SU2 breaks into human electromagnetism. So this way, the bosonic sector contains three gauge fields. There are three gauge fields and three component Higgs field. They also consider a triplet for Higgs. And the third component of this W3 they identified with the electromagnetic field. Tried to identify with the, and others two are W plus. Those heavy curves because it's not consistent with the Big Bang synthesis and observation. So it can be done by inflation. I have not talked about intermediate scale monopoles. They can have testable prediction around 10 to the 11 JeV or so. And then there are people have also talked about depth scale monopoles, and which can be detectable in MoEDAL or future colliders. The detection of monopoles will open up a new window to link it to the new physics beyond standard model. Thank you.
Target love. You're the battles won, it's your kingdom come. Best to give me.
This is the cross-section as a function of mass. As you can see here, it's a tevatron. 2 TeV set of mass energies, TT bar production, about 8 picobar, and it's a mass of 173. The arrow bars show, of course, the accuracy with which you can determine the mass using this. And this is used the pole method because it's a sort of the if you do the cross section, then it is at the pole, and that's a different way of getting at the mass. If you let the mass slide, you see that when you hit the pole, the function, then you are at the peak of that mass. Yeah? The mass is, of course, we'll talk about it later. This is one of the methods to find out. But let's move on. This is now the corresponding data with Atlas and CMS, a different set of mass energies at the LHC, 8 TeV and 13 TeV. First of all, you might think, isn't it more interesting to see the only data at the highest energy? And I say, no, not at all, because in the end, what you want to do is you want to test very accurately your theoretical descriptions, and then it is very good to have lower energy data as well. The highest energy data, of course, are also meant to look for the new physics. They are all compatible with next to leading order calculations, and they are all of similar precision, here you see. I will not go into the detail, just remember them. Again, compares wonderful with PowerHack and so Monte Carlo predictions, which always have a fundamental model of production plus hadronization model. And then you see those different Monte Carlo generators giving you a very good description of the data. Here you see from CMS a different variable again. You don't need only to take the invariant mass, but you can also look for the rapidity of the top quark. You can reconstruct that. The rapidity is the measure of the angle with respect to the beam direction. If the angle is small, that means the production goes very much in the forward direction of a certain particle, its rapidity will become large. Yeah? So at large rapidities, it would mean that you have a TT bar system where one top goes very much in one direction of the beam and the other one in the opposite direction. This number of events is not as high as the central production here. It's almost like an isotropic reconstruction. But again, this tests, of course, your models, your QCD models, and in the end, the Parton distribution function. The conclusion here, PowerHack plus Pisa gives the best description of data. But this is always with a grain of salt. I mean, there are other event generators which are very successful in other events. Yeah. What I wrote here, double differential measurements reveal some discrepancies between data and Monte Carlo. This is not something where we need to really put our focus on. That's why I didn't add it here. It is not a sign of new physics at the moment, it's just a question of the description. If double differential means you subdivide the data sample into two different entities like rapidity, PT, or whatever. Now you can subdivide those data, and then you can have distributions again. So let's look into some subject which has been quite interesting a few years ago. I mean, it's still interesting, but it was even somehow raised serious discussions about our modeling of TT-bar production. That is looking at the so-called asymmetry. If you, this is something very interesting. Nobody would expect it. If you think, well, you have it started with proton-antiproton collisions, so you have a valence quark and an antivalence quark, and they annihilated into a virtual muon and then produced a TT-bar pair, then you would think this, the TT-bar pair should not have any memory to where was the direction of the quark and where was the direction of the antiquark. Yeah? That's at tree level, this is of course correct. But when you look at higher order QCD, then you indeed start having effects from muons being radiated from an incoming quark or from an incoming antiquark. So let's stay at the moment with the production of the top quark pair from GQ-bar annihilation. As you know, at the LHC, you have one valence quark and most times one valence quark, one C quark, sometimes one C quark and one C antiquark to produce TT bars. But we now are still at the teratron, where you have quark, antiquark from each so the quarks come dominantly from the proton, the antiquarks from the antiproton. So there is sort of already an asymmetry in which quark comes from where. Yeah? Here we have the quark from the proton, here we have the quark from the antiquark from the antiproton. They produce the TT-bar pair. And of course, this diagram here is absolutely neutral. It doesn't reflect the orientation, the original direction of the quark or the antiquark. But if you add higher orders, then here, so these are the fundamental diagrams, this is higher order, then you get an interference effect, and that produces, that sort of displays the memory of the direction of the quark and the antiquark.
Loyalty, 'cause I'm taking the world, you'll see. They'll be calling me. They'll be calling me royalty. Best to give me loyalty, 'cause I'm taking the world, you'll see. They'll be calling me. They'll be calling me royalty.
So what is the mission of CERN? It has science, to know secrets of the Big Bang standard models and QCD after the Big Bang, like that technology in different areas like accelerators, detectors, and computing, and in dosimetry and also in medicine, then training different areas and application in different fields. So what types of science at CERN? Just at CERN they study at the quark level, and after the Big Bang, the matter was in the form of 2D plasma, and then photons and neutrons, and then low mass nuclei, and then here. So the major discoveries at CERN are the Higgs boson, and then the Muon and Z boson, and multiplied that, and then we use the terms that was prediction, currently prediction by Professor Islam. So, this is accelerated complex, and here are two sources, region 2 and region 3. And one is for the proton source, another for heavy ion like electrolyte source. And then from the source, the beam is directed to booster, proton booster, and then to proton synchrotron. And then from proton synchrotron, the beam goes to the super proton synchrotron, and then towards the Gauss segment. Right? And there are 4 experiments with at LHC, and there are other non-LHC experiments that are at the SPS and BS. And Pakistan is contributing in LHC experiments and in non-LHC experiments. So, in the next slide, we can see how from cell the beam goes from the source towards the boosters, towards the proton synchrotron, and so this is the source for protons, and from proton the beam goes to the LINAC, and then in the proton synchrotron, and then proton synchrotron booster, and from here it goes to super proton synchrotron, and the energy goes to the BeV range, and then the super proton synchrotron that is 6 kilometer in radius, and here one. And you can see these are the magnets that are, and then this is the large hadron collider, and 4 major experiments here. And this is the tunnel at the end of the meter below the ground, and the CMS experiments. 2 particles collides, and large data is collected, and that is saved in different grades and computers. So it has many applications. I will talk here a little bit about just so I mention about one slide because you are already familiar about basic research. And CERN is not only contributing to basic sciences, but it also contributing to applied sciences, and also to those areas that are useful to society, like the accelerated detection used for radiotherapy with protons, ions, and with electrons. And then PET technology at CERN is used to for medical imaging and diagnostic. Then pixel detection techniques are used for high resolution 3D X-ray imaging. And then the last one is CERN produces innovative radioisotopes for nuclear medicine and research. So Pakistan Institute of Nuclear Science and Technology is at the moment is contributing in this area that I will talk about a little bit at the end. So what are the major achievements of Pakistan collaboration? The first collaboration agreement was signed in 1994 after approval from the cabinet government of Pakistan. And then in 1997, an agreement was signed with CMS, and in 1999, NCP became member of CMS experiment. Then there were 2 major protocols at CERN, one in 2003, and 5 million Swiss francs were given to CERN for different projects, and then in 2006, and the 5 million more Swiss francs were given, and then in 2012, Council became member of LHC experiment, and in 2015, Pakistan became associate member of CERN, and then 17 Eastern became associate member of LHC experiment, and then 20 Eastern became member of the medicine experiments, that is for radioisotope protection. And then for last 2 years back, the 5-year deal was conducted, and Pakistan has granted associate membership status for next 5 years.
तो कैमरामैन को कहा लेकिन वो अभी टाइम नहीं।
Thank you very much. Now
Now I would request Dr. Zafar Yaseen to please come and take your shield. Thank you very much. So,
There was not that much. I can tell you how much actually. So at the time when the Big Bang happened, lots of antimatter was produced. Lots of matter, lots of antimatter. It's just that it's all annihilated and some matter is left over. But only 1 in a billion matter is left over. So the rest, billion times as much matter that we have here now, the rest annihilated. And the reason we know this is that you can look at the large, see how many stars there are, that's matter. And then you can measure the cosmic microwave better.